Hello everyone. In the previous class, we have discussed about expressions, operators, and operands, and we have also discussed the different type of operators, and we have covered arithmetic operators, logical operators, and relational operators. We'll continue from there onwards. The first one is the equality operators. So equality operators are there are four different equality operators are available. That is a logical equality, logical inequality, case equality, and case inequality. So you can observe the symbol used for the logical equality is equal to sign, that is 2 times is equal to sign, whereas for inequality exclamatory sign followed by is equal to, it represents the inequality. There is another type which is called as case equality, in which 3 is equal to sign are used, and the case inequality symbol. So we will come to know what is the difference between the logical equality and the case equality. You should be able to see the difference of these two types. When these equality operators are going to be used in any expression, they are going to return the result in the form of true or false. That is, logical value 1 represents the true value, and if the value is 0, the result is false. In the first two cases, that is logical equality and logical inequality, if any value is unknown or if any value is high impedance, that is x or z is present, then the result may be x. That is, true or false will not be the result is unknown. If any value in the operands which consist of x or z, the result is x. Whereas the last two, that is case inequality and case equality and case inequality, these two produce only true or false result. There is no unknown result. So that is the difference between the first two and the second two. So these operators compare the two different operands, left hand side operand and right hand side operand. They are going to be compared bit by bit. If the operand size is not going to match, then the zero filling will be done here to match the operands. So these operators compare the two operands bit by bit with zero filling with the operands are of unequal length. If to make the equal length in size, equal length of the operands, the Verilog HDL fills 0. So there's a table here, so which represent the list of operators. So expression, you can observe the operands are used: A, logical equality, B. So what it does is, if A equal to B, then the result is true. If A is not equal to B, then result is false. If any one operand, any one bit of A and B consists of unknown value x or high impedance value z, then the result will be unknown, that is x. The second one, A is not equal to B. So A is not equal to B, when it is used in an expression, the result is true if A and B are not equal, then the result is true or 1. If A and B are equal, and if you are comparing for A is not equal to B, then result is false or 0. And similar to the previous one, it produces x result or unknown result if any bit in A or B consists of the unknown value or high impedance value. Now see the case equality operator. A 3 times is equal to operator. So here it is important to note the difference between the logical equality operator and the case equality operator. So the logical equality operator is going to produce the result only in terms of true and false. So possible result is 0 or 1. And the last one is A not equal to B, that is in case not equality it is. So a not equal to B including X and Z, the result is 0 and 1, 0 or 1. So the same description is given here. The first two we have discussed. The second one, case equality. Here what happens is the bits are compared bit by bit in case equality also, and it compares for the values of X as well as Z. It compares if any bit that present in the operand, if any bit is unknown, and in the same position of those operands, if both the operands consist of unknown value, then that it is going to be compared unknown value also. And in that position, if the unknown value are there, then the result based on that, whether true or false, will be produced. So the what happens is compare both operands bit by bit, and all the bits, compare all the bits including the X and Z along with 0 and 1. So the result is going to be 1 if the operands match exactly. If the operands in A and operands in B match exactly including X and Z value, the result will be 1 or true. The result is 0 if the operands do not match exactly. The result will be 0 or false. The case equality operator never result in an X. That means it produces only true or false result. It will not produce X result or unknown result. Here there are examples on equality operator. Suppose consider A is equal to 4 and B is equal to 3. These are the decimal numbers. A equal to 4, B is equal to 3. X is a 4-bit binary number 1010. Y is 4-bit binary number 1101. Z is 4-bit binary number 1XXZ. M is equal to 4-bit binary number 1XXZ. And N is equal to 4-bit binary number 1XXX. Now we will check the equality operators with this example. First one is the A is equal to B. Now observe A and B value. A is 4, B is 3. So A is not equal to B here. So the result is false. So result will be logical 0. X is not equal to Y. Observe X and Y. X is 1010 and Y is 1101. They are not equal and we are comparing not equal. X is not equal to Y. Yes, it is true. So result will be logical 1. Third example, X equal to Z. It's again logical equality operator. X value consists of 1010 and Z value consists of 1XXZ. As the Z value consists of X and Z value, the result is unknown here. We cannot compare the unknown value with the bit in logical equality. That's why result is X. Now Z is equal to case equality operator M. Z case equality operator M. Now just check Z and M. Z is 1XXZ and M is also 1XXZ. So in the case equality operator, it will check bit by bit all the bits including X and Z. So the position of Z and X in both operands Z and M are same. So least significant bit is Z and next two bits are XX and the most significant bit is 1. So they are exactly matched. So result is 1. All bits are matched here including X and Z. Now compare next example, Z case equality n. So Z and n. Here one XX matches from the most significant bits, but the least significant bit do not match, because in Z the least significant bit is Z itself, that is high impedance value, whereas in n the least significant bit is X. Z and X do not match, that's why Z is not equal to n, that's why it's a false. So result is logical 0. So here LSB does not match. And last example, M is not a case inequality operator n. So M and n, they do not match. You can observe there, M is 1xxz, whereas n is 1xxx. They do not match. So we are comparing for inequality. So it's true. So logical result will be logical 1. Now see the bitwise operators. So bitwise operators, there are total 5 bitwise operators. The negation, this tilde sign, AND operator, single AND, OR operator, XOR, that is cap, then XNOR. Either you can use cap tidal or tidal cap, both are same. So these are the bitwise operators. So bitwise operators perform a bit by bit operation on the two operands. There are going to be two operands, left hand side and right hand side. In between the operands there will be operator. So these bitwise operators will be placed there. So they are going to be operate by performing the operation, particular operation, bit by bit. So they take each bit in one operand and perform the operation with the corresponding bit in the other operand. If one operand is shorter than the other, it will be bit extended with the 0 to match the length of the longer operand. So if operands do not match, if one operand is longer and another operand is shorter, so shorter operand will be made equal to longer operand by filling 0. So in the next slide there is a table which gives you the truth table for the bitwise operators. So same kind of table it is, that is NOT gate, AND gate, OR gate, XOR gate, XNOR gate, including the value unknown, X value. So here Z is treated as an X in a bitwise operator. Remember here, if any high impedance value appears in a bitwise operator, that will be treated as unknown value itself. So the exception is unary negation operator, that is a single operand is used here for the negation, tidal sign. So it operates only on a single operand, so operates on bits of the single operand. Remember here, that is a negation. Other operators, other bitwise operators, that is AND, OR, XOR and XNOR, operates on two operands. So these are the truth tables for the bitwise AND operator, bitwise OR operator, bitwise XOR operator and bitwise XNOR operator. Also the bitwise negation. Bitwise AND operator, as you know, 0 and 0 is 0. Any one bit is 0, the result is 0. If all the bits are 1, then only the result is 1. If unknown value is ANDed, the result is unknown. Similar to OR operator, if any one value is 1, the result is 1, otherwise the result is 0. If you OR with 0, the result is X. If you OR with 1, the result is 1. If you OR with X, the result is X. XOR operator, 0 0 0 0 1 is 1, 1 0 is 1, 1 1 is 0. That is, if odd number of ones are present in the operand, then the result is 1, otherwise 0. For unknown value, the result is unknown. Exactly, complement of this one will be the XNOR operation, bitwise XNOR, and the negation, if the 0 is the input, it operates only on the single operand. That's why if the operand consists of 0, the result is 1, and vice versa. For 1, it's 0. If unknown value is there, then result is unknown. We will see the examples. X is equal to 4-bit binary number 1010, and Y is 4-bit binary number 1101, and Z is 4-bit binary number 10x1. Now negation of X. X is 1010. So negate all the bits. So 1010 will result in 0101. So 4-bit binary number 0101 is the result. X and Y. So X is 1010, Y is 1101. Bitwise AND operation. Perform the bitwise AND operation. So 0 1 is 0, 1 0 is 0, 0 1 is again 0, and last most significant bit 1 1 results into 1. That's why the result is 1000. 4-bit binary number 1000. Then next example, 1 X or Y. Bitwise X or Y. So again here perform the OR operation on X and Y values. So result is 1111, because all the bit position consists of at least 1 1. Then XOR operation, X cap Y, XOR operation. So 0 1 is 1, 1 0 is again 1, 0 1 is 1, and most significant bit both are 1 1. Even number of ones are there here, so result is 0. So 0 1 1 1. XNOR operation on X or Y, exactly the complement of XOR operation. So previous result was 0 1 1 1. Now complement it 1 0 0. Now X and Z. Now observe here, Z value consists of unknown value 10x1. So that bit result into unknown value. So 0 and 1 is 0. X value is 1 0 0 1 0 1 0. That's why 0 and 0 is 0. 1 and X is X. Then 0 and 0 again, the result is 0, and last bit 1 and 1. 1 and 1 is 1. So as the second bit consists of X in the value Z, the result is in that position is X. So here there is one more distinguish. Previously in the previous class we have discussed about the logical operators. Now we are discussed the bitwise operator. Here the thing is, the operators used are same. That's why it is very important to distinguish bitwise operator and the logical operator. You can observe here, bitwise operators are negation and OR, single time they are used, whereas in the logical operator the negation sign is different, exclamatory mark is used, whereas AND operation 2 times AND symbol is used, and for OR operator 2 times OR operator is used. Again there is one more difference. Logical operator, previously whatever we have discussed, those are the logical operators. They are going to result into single bit true result, that is 1, or false result 0, or the unknown value X. But here in the bitwise operator the results are bit by bit. So multiple bit value will be the result. It is not a true or false. So logical operators perform logical operation and not a bit by bit operation. So to differentiate the logical operator and bitwise operator. There's an example here. X equal to 4-bit binary number 1010 and y is equal to 0000. Now if you use a bitwise operation on x and y, observe here the bit by bit result is available. Result is 1010, that is OR operation. Whereas if you do the logical operation, then observe here, as x consists of some value other than 0 and y consists of 0, so logically x equal to 1 and y is equal to 0. So 1 or 0 is 1. That's why the result is true. So this is how we can differentiate between the bitwise operator and the logical operator. Next one is the reduction operator. Now again here in the reduction operators, the similar kind of operators are used. That is, reduction operators are AND, that is single AND operator, NAND, tidal sign followed by AND operation, OR operation, NOR operation, XOR and XNOR. So these are the operators present in the reduction operator. Now here the difference between the reduction operator and other operators, that is logical operator and bitwise operator, is in those there are two operands, but here in the reduction operators it take only one operand. It operates on a single operand, whichever may be it is AND operation, NAND operation, OR, NOR, XOR and XNOR. All these 6 operations performs on a single operand or only one operand. So reduction operators perform a bitwise operation on a single vector operand and yield a 1 bit result. The result is 1 bit here. So we can see the truth table here. The truth table is exactly similar to the previous topic, that is bitwise operator. So in the bitwise operator we have seen AND, NAND, OR, NOR, XOR, XNOR operation. So the result truth table is same. The difference between the bitwise operators and reduction operator is, in the bitwise operation the results on bits from the two different operands, whereas here, as we already discussed, the operations are on the bits of the same operand. So the reduction operator works bit by bit from right hand side of the operand to the left hand side, bit from right hand side to the left hand side of the same operand. Reduction NAND, reduction NOR and reduction XNOR are computed by inverting the result of the reduction AND, reduction OR and reduction XOR operation respectively. That means, so in the previous cases there were NAND and NOR were not available. So how to get those results here? That is, to get the result of the NAND, just complement the reduction AND result. Similarly, for the reduction NOR, just complement the reduction OR result. And for the reduction XNOR, just complement the reduction XOR operation. Now we will see the example here. X equal to 4-bit binary number 1010. Now perform reduction AND operation on X. So X is 1010. So how to represent this one? Just check here how to operate. So it is equivalent to 1, that is most significant bit 1 and 0 and 1 and 0. So in the reduction operation it is going to be like this. All the bits in the same operand you can use and operate, find the value like this. So from the least significant bit 1 and 0 is 0. That result 0 and 0. Again the result is 0, and 0 and most significant bit 1 is again 0. So result is 1 bit binary 0. Next, OR operation on X. So it is equivalent to 1 or 1 or 0 or 1 or 0. So perform the operation from the left hand side. 0, that is least significant bit, or 1, the result is 1. That result 1 or 0 is again 1. Then result 1 or most significant bit 1 or 1 is 1. That's why the result is 1 bit binary number 1. XOR operation X. 1 XOR 0 XOR 1 XOR 0. 1 XOR 0 is 1. Result 1 XOR 0 is again 1. Now 1 XOR the most significant bit is 1. 1 XOR 1 is 0. That's why the result is 0. So a reduction XOR XNOR can be used for even or odd, that is parity generation of a vector. So here again we are discussing the same thing, the use of similar set of symbols. So in the logical operator we have used this exclamatory mark, double and sign, and double OR operation, whereas in bitwise tidal sign, and operation, OR operation, and cap, that is XOR operation. And in the reduction operation, and OR and cap again is somewhat confusing, is it? But as now we have discussed all the three types, logical operator, bitwise operator, and reduction operator, we can easily differentiate all the three. The first one, logical operators, give you the result in the form of single bit, that is true, false, or unknown value, whereas in the bitwise operation the result is bit by bit. Here in both the cases, logical and bitwise, the operators used are, operands used are 2, whereas in the reduction operation it performs only on the single operand. So the difference lies in the number of operands each operator takes, and also the value of the result computed. Next one is the shift operators. So shift operators are four different type of shift operators are there: right shift, left shift, arithmetic right shift, and arithmetic left shift. The symbols are shown for the right shift, left shift, arithmetic right shift, as well as arithmetic left shift. So the regular shift operators shift a vector operand to the right or left by a specified number of bits. So we are going to specify the how many number of bits it has to be shifted, either right side or left side. So like that vector operand will be shifted to the specified side. The operands are the vector and the number of bits to the shift. When the bits are shifted, the vacant bit positions are filled with 0. So suppose if you shift the bit by right side by one position, then left hand side one bit will be vacated. So that vacated bit will be filled with 0 in the right shift operation and also in the left shift operation. That means shift operators do not wrap around. So remember here, shift operators do not wrap around, whereas in arithmetic shift operator they use the context of the expression to determine the value with which to fill the vacated bits. Here we do not consider that the 0 itself will be filled. So it depends upon what is the position of that bit. That means what is the bit, either it is 0 or 1. If it is 0, it filled with the 0. The vacated bits are filled with 0. If it is 1, the vacated bit is filled with 1. The examples: x equal to 4-bit binary number 1100. Y is equal to x right shift one time. So x is 1100, shift right side one time. So least significant bit 0 will be vanished. Right shift all the other bits right side by one bit or one time. So most significant bit will be vacated, so that vacated bit will be filled with a 0. So the result is 4-bit binary number 0110. Second example, y is equal to x left shift 1. So x is 1100, left shift operation. So shift the x value left side by one time. So most significant bit 1 is vanished here. All the other bits are shifted one time left side. So that is 1000. Least significant bit is vacated. So that vacated bit is filled with 0. So the result is 1000. Third example, y is equal to x left shift 2 times. So x value is 1100. So left shift it 2 times. So most significant bit 1 and its next bit 1, both are left shifted. So both are vanished here, 1 1. Other values, other bits 0 0 is shifted 2 times left side. 2 positions are vacated, least significant bit and its next bit, both are vacated, so filled with 0. Result is 0000. Now there is one more example on arithmetic right shift. So integer a comma b comma c, so these are signed data types. A is equal to 0, b is minus 10. So minus 10 is represented in 2's complement form, so that will be 10110. These are the least bits, other bits are 1. Then the expression c equal to a plus b right arithmetic shift by 3. So arithmetic shift, right shift it, so 110 will be vanished here. The remaining is 10. Shift them all to their original position and fill the remaining bits by the last bit. So the result will be minus 2. That is, in decimal it is minus 2 due to the arithmetic right shift operation. So thank you for watching the video.